I'm going to present Strut Modeling. Strut Modeling is a project done in collaboration with the University of Hasselt, with Ramakers, who's also here, and Kris Luyten. So Strut Modeling is a low-fidelity construction kit that consists out of struts and hubs. What the user can do is they can just simply connect a strut to a hub and build in the physical space. In the background, you can see that struts are tracked in real time in a virtual environment. When the user builds a 3D object in the physical space, he does not need any 3D modeling skills. In the next couple of slides, I'm going to talk about how we design a laptop stand with our strut modeling techniques. Right. What the user does is he starts by connecting struts to hubs, and by building in the physical space, he can adjust the struts to fit around a laptop in this case. He can adjust the width, the height. He can also build 3D geometries, as you see right there, and he can test them during the design phase. So once he's roughly satisfied with the model, he can test the model next to an external monitor, and he can see for himself if the laptop stand is at the right eye height in comparison to the external monitor. So he positions the laptop on top. If it's not the case, if the height or the angle is not right, he can adjust the struts by turning the thumb wheel on the strut. Once he's satisfied with this model, we have this virtual rendering environment where our object is automatically in track. And what he do is he has different post-processing steps. In this case, we choose a reinforced wireframe model of our strut model. After this is done, he can export this as an STL file that's ready for 3D printing. So once this model is 3D printed, he can check the angle and the height that's already tested in the design phase. And we have, in this case, an ergonomically sound laptop stand from the first 3D print. So in short, strut modeling uses struts and hubs to build a physical object. The hubs are magnetic and the struts are actively communicating to the central hub. The users can adjust the strut's length to model around physical objects. So you can build in physical space and use the struts to adjust according to the physical models that you have. Every strut is tracked in real time and is being rendered in a virtual environment. All right. In contrast to other construction kits, a lot of research has been done in digitizing physical objects. For example, what you can see here is Maker's Mark. It uses clay to sculpt 3D models, and then it's digitized by 3D scanning. The downside of using clay is that it requires a lot of crafting skills. To resolve this, other researchers have explored construction kits. We have two general types of construction kits. First, we have the struts and hubs, and on the right side for you guys, we have the brick kits. I'm going to go into a little bit more detail. The struts and hub kits, like the work of Jacobson at your left, and the work of Weller with Bussey on your right, uses struts that snap to mechanical hubs, and they make skeletons of their struts and animate 3D figures in a virtual environment with this. The benefit of this is that you can animate them by hand. The downside of using these struts is that they have a fixed number of struts that can connect to a central hub. With our strut modeling technique, we can connect an arbitrary number of struts to a single hub because we use a magnetic hub. The second type of construction kit are brick kits. For example, on the left we have Duplo-Track, and on the right we have the work from Anderson et al. Both of these kits have a Lego-like or Duplo-like brick kit that is tracked, and they recreate these bricks in a virtual environment. When using these brick kits, for example, if you want to model a rooftop, like you see on your left, if you want to change the angle, you have to deconstruct all the bricks to adjust the angle. So in general, strut modeling contributes a minimalistic kit consisting of only one strut and hub design. To avoid puzzling with many types of pieces often experienced in existing construction kits. Now, how do we do this? We have a central node that is connected to a computer that runs a virtual environment, and then all struts are actively communicating to the central hub, and the magnetic hubs are completely passive. So a single strut exists out of the base and an extension. The base is here. The base is 93 millimeters and the extension is 77 millimeters. We can extend this strut by turning the thumb wheel. This is speed up this video. You can turn up because we have very fine pitch in our strut. We measure this with a rotary encoder at the back of our strut mechanism. We count the pulses of every revolution with this rotary encoder. So at the end of every strut, we have a metal connector that attracts the magnetic ball, so we can build physical models. It provides the mechanical strength. And they also are used to detect adjacent struts. I'm going to talk about this more later in the slides. What we've developed is a custom PCB, and it contains a microcontroller, and the main part for the tracking is done by the IMU, the 6-axis IMU. All right. Every strut also is equipped with a wireless communication module that communicates with the central node. Every strut is also equipped with a Lipo battery. The Lipo battery powers the strut. It's just 130 milliampere hour battery. We also developed a little battery management PCB to provide the necessary power to our strut. Right. This hardware implementation, we realize real-time relative position tracking of our struts. This is done by combining relative orientation data with topology information to get relative positioning. First of all, we have the relative orientation. We do this. We calculate the relative orientation with the 6-axis IMU. We combine the accelerometer data and the gyroscope data, and we continuously stream this data of every strut to a central node. Once we have this relative orientation, we need the topology information. And when we combine the topology information and the relative orientation, we get a relative positioning. So to get this information, the system continuously goes through the following procedure. So here we have a couple of struts where the central node sends a message to one of the struts, and it tells it to apply a voltage on one or the other side of its strut. In this case, it applies it on the left side of the strut. Once this voltage is applied, it starts a signal, it sends a signal to all other struts to start reading if they can find any signal on a magnetic hub. So once they detected a signal, if there's a voltage present at one or the other end of its strut, then it will report back to the central node. Then the cycle repeats, and it will apply a voltage. The central node says apply a voltage on the right side of your node, and the central node says start reading on all struts. By doing this, we can build up our topology information. This cycle repeats constantly. We can scan the full topology information from about 20 struts, I think in less than a second. So When we combine the topology information and relative orientation for every strut, we get the relative positioning. And this is sent to the virtual environment where the 3D model is rendered in time. In this rendering environment, we can choose 3 different post-processing steps for the digital fabrication processes. I'm going to try to explain these post-processing steps with this cookie jar as an example. So we built this cookie jar with our strut modeling technique, and once you've built it, you have a virtual representation that's on your left in the rendering environment. And the first option is to export it as a reinforced wireframe model. So the position of all struts are rendered as cylinders and then combined in a smoothing operation. This will result in a 3D model that can be exported as an STL file, whereafter you can 3D print it. What if you want an enclosed 3D model? We have the second option. We can do a convex hull operation on the strut models. We can thicken the object or export it as a single shell model for 3D printing. Right. The last option is, in the last option, we project the vertices of the convex hull onto a 2D plane, and we can export this as an SVG file. This then can be used for laser cutting or CNC milling. So with this technology, novices can easily produce a wide variety of artifacts. To demonstrate these possibilities, we produced a laptop stand, a cookie jar, a photo stand, and some assistive tools. Alternatively, strut modeling can also be used to measure angles or lengths. For example, to repair the top lid of this trash can, we can measure the angle or length that can be automatically applied to a parametric model of the top lid. So to conclude, in this paper we presented a universal hubs and struts system where an arbitrary number of struts can be connected to one hub and where the length can be adjusted. With strut modeling, the user can build objects in physical space without the need of 3D modeling skills. And the users can build around existing objects, allowing them to adapt and test the object in the design phase. Once satisfied, the model can be exported and produced by digital fabrication, and the printed or laser cut model can be immediately used as it was already tested in the design phase. Right. I want to thank you for your attention, and if there are any questions, I'm happy to answer.
Hey, great project. I'm Sai from Carnegie Mellon University. One of the questions I had was struts are typically used for resisting compression. I mean, they're typically used in chassis and like airframes and so on. I was wondering if you considered like doing any kind of compression testing on your final fabricated object or giving feedback to the user as they're building these trusses.
Yeah, so we didn't implement it in our software or hardware. It's for sure a possibility to implement that in the future. I think that's very useful. Yeah.
All right, let's thank Danny and all the other speakers in this session again.